Hey, it's Alpine Math and History, and we are going to take a look at the lift equation. So we're going to tell you why we're making this video in the first place, but what we're going to do is give you a lift, and we're going to help you understand what the lift equation is. So when you think of lift, what do you think of? Well, since I'm really into airplanes, and since this channel is really called Helping Airlines Math Industry, when I think about it, you see this airplane right here? In order for this plane to fly, there has to be four natural forces of flying, or four natural forces of how the plane flies. The one that goes up, that lifts the airplane up, is going to be called lift. The one that's pulling you down is called gravity. Airplanes cannot land unless they have some kind of gravity or something that pushes them down. What pushes them forward is going to be thrust. And what pushes them back is going to be drag. But today we're going to understand how we can understand lift equations. So there are going to be two parts of the video. The first one right now is going to talk about the formula and how it is calculated. The second part of the video is going to talk about how to solve for the equation using actual numbers for it. But the problem is we're not going to actually reveal the numbers right now. An airplane flies over your house and airdrops a drone to you. You want to understand and ask how much lift and force is applied on the airplane's wing, and it's going to be measured in kilograms per meter cubed. So when pilots and engineers measure lift with helicopters and airplanes, they usually measure in kilograms per meter cubed. So there's an actual formula to help us understand how to calculate the force applied on the airplane's wing for lift. And here it is. We have L equals CL times 1/2 of P V squared ms. What we're going to do next is understand what these mean. So I'm pretty sure we understand that the L is what we're trying to look for, the lift. 1/2 of P is going to represent the air density. The V squared is going to talk about the true airspeed of the airplane. And S represents the surface area of the airplane's wing. Very important. So what we're going to do is explain why these are a factor of lift and how they can be changed. But hang on, there's one more variable that we forgot. And it's the hardest to understand in this equation. It's called the lift coefficient. So let's understand what each means. Let's go from, well, we already know what lift is, the force that wants to make the airplane go up in the sky. But let's go from backwards to forwards, because that seems to be a bit easier to understand. For example, the surface area of the wing kind of makes a lot of sense, because if you have a wing like this, and it can just generate lift. If I change the size of how much the wing covers in the surface area, so in other words, what we're trying to say is an airplane needs to have some kind of wings so it would be able to fly, and it would beat the airplane's weight. For example, you see this Boeing 757 right here, the model, China Southern, the airplane that I came home from China, or one of the airplanes that came home from China. So imagine having a Boeing 757. If I took the wings off and replaced them with the wings of a Learjet 45, a tiny private jet, the problem is there is not a lot of wing that would cause the 757 to actually go in the sky and create lift. The body of the airplane would be too heavy, therefore it won't be able to fly. So it doesn't make sense if Boeing puts tiny wings on a jumbo jet. There's not enough surface area and there's not enough lift. So that's why surface area is important, because we need to find some kind of way to generate lift that beats the airplane's gravity. The second one, v squared, is going to talk about the velocity, or what they say, the airspeed. And this is actually one of my favorites, because what if I told you that the airplanes don't actually go 500 miles per hour? And there's a reason why. And the other crazy thing is, the International Space Station up there is actually not flying truly at 17,000 miles per hour. There is an exact idea, and there's a reason why for this. So say this red line is the ground right here. As you're taxiing to the runway, it probably should take 20 miles per hour at most. But the thing is, most commercial aircraft, like this right here, but also this right here, say that they fly 500 miles per hour. But the problem is, there are two variables. The two variables are